Hello, good morning, later entry students. So now we are going to discuss about general mechanism of aromatic electrophilic substitution reactions. So we already discussed about the benzene structure, how we can define the benzene structure, how the Kekulé structures proved that it is correct, and it is having delocalized pi electrons. So that's why the benzene ring is showing mono substitution reaction and disubstitution reactions, that is they can give ortho meta para disubstituted compounds. So during aromatic electrophilic substitution reactions, aromatic, so benzene is aromatic, it is having delocalized pi electrons, so it is an aromatic structure. Electrophilic substitution, why benzene is undergoing electrophilic substitution means benzene is rich of pi electrons, so it can readily gives electrons to electrophile, electron deficient compound. So that's why it undergo electrophilic substitution reactions. Coming to the word substitution means one of the hydrogen is removed and another atom, chlorine, bromine, nitro, sulfonated molecule or any can be substituted. That's why we are saying aromatic electrophilic substitution reactions. So these electrophilic aromatic substitution reactions involved in replaced by hydrogen atom of aromatic ring by an electrophile. See like this. So one of the hydrogen atom which is present on the benzene is replaced by the electrophile. So that's why it is a aromatic electrophilic substitution reaction. So in presence of any catalyst it can take place. All electrophilic reactions follow the three steps mechanism. The step 1 is formation of an electrophile. The electrophiles are either positive ions or some other electron deficient species with large partial positive charge. That means electrophile means electron deficient atoms, electrophiles. So that can be developed by the first step. So the compound like this HCl. In presence of any catalyst it can give H plus and Cl minus or Cl2. One of the Cl plus and one of the Cl minus. Cl plus is the electrophile that can be substituted, it can give chlorobenzene. So that is the production of electrophile, first step. Second one is the step 2. The electrophile attacks the aromatic ring to give an rhenium ion. This is a very important step. The electrophile which is formed that can be attacks on the benzene ring to form a rhenium ion. That is, electrophile attacks the pi system. Pi means pi electrons, that is delocalized pi electrons present in the benzene ring. Pi system of benzene to form a rhenium ion. In step 2, the electrophile takes 2 electrons of the 6 electrons per system to form a pi bond to one carbon atom of the C6H6 ring. Formation of this bond interrupts the cyclic system of pi electrons. In the formation of rhenium ion, a carbon atom that forms a bond to the electrophile and sp3 hybridized and thus to no longer has an available p orbital. Now only 5 carbon atoms of rings are still hybridized and still have sp2 hybridized p orbital. The 4 pi electrons of rhenium ion are delocalized through these pi orbitals. So the above all these things explains that what benzene containing 6 carbons. Carbon is hybridized as a sp2 hybridized state. sp2 hybridization means what? Carbon is having 6 electrons, that is 1s2, 2s2, 2p2. So 2s2 containing 1 electron is coming into the sp3, 1s1, 1s2, 2s1, 2p, 3 form. And now the 2s1 containing single electron and 2 electrons which are present on the p orbital, these two undergo sp2 hybridization. So 3 are involved, 1s, 2p are involved, so that these 3p orbit, the sp2 hybridized orbitals undergo hybridization to form 3 sp2 hybridized orbitals, and they can form single bond only. Always single bond with 2 hydrogens and single bond with 1 carbon. Like this, 1 carbon and another hydrogen and another carbon. These 1, 2 and here is one hydrogen is there. This sp2 hybridization takes place. But another p orbital containing only one electron, that is having a dumbbell shape. Each carbon is having one single pi electron. So each p orbital sp2 orbital containing one single electron each, like this. So these all the 6 electrons are undergoing the delocalization of pi electrons. So during substitution, this electron can be readily given to that electrophile and it can getting the positive charge. So this double bond is breaking takes place and it can, and this carbon is sharing electrons to the another electrophile, and this is the positive charge taken place by the single carbon. And next what happened, this carbon is also having dumbbell shaped p orbital containing one electron. So this electron is taken by this carbon and given to this, and now it is getting the positive charge. So in the same manner, again this carbon is taking electron from the side carbon and it given to this carbon, and here it is getting the positive charge. So this rhenium ion also delocalization takes place. So this is the resonance stabilized rhenium ion. So after electrophile can attacks on the any carbon, that carbon which is having side carbon having p orbital containing one electron is taken by this carbon and given to the electrophile, and this, because of giving of this electron, this carbon is getting the positive charge. So this can be delocalized in this manner. It is the rhenium ion formation takes place. So the coming to the last step is removal of proton from a rhenium ion to give a product. So this is the resonance stabilized one, and so what happened is hydrogen is having one electron. So this electron is given to this carbon and the hydrogen is gone out as a H plus ion, another electrophile. So that is called electrophilic substitution, and the benzene, it can fulfill the delocalization of pi electrons and it can stabilize. So due to the electrophilic substitution, the benzene ring is stabilized. Whether if it is addition, the bond can be breaking takes place and it should not be stabilized. So that's why benzene undergo electrophilic substitution reaction. The third step is, that is a simply removal of the proton and donating electron to the ring system and maintains the delocalization of pi electrons. The two electrons that bonded to this proton to carbon becomes a part of the pi system. The carbon atom that bears the electrophile becomes a sp2 hybridized again, and a benzene derivatives when 6 fully delocalized pi electrons are formed. So like this, the hydrogen can be removed and that electron is given to the benzene ring, and again stabilized electrophilic substituted benzene compound formation takes place. So these are the reactions, simply how the electrophilic substitution reaction takes place. Simply nitration. So nitration is done in presence of nitric acid mixture, that is H2SO4 and HNO3 at 50 to 60 degrees Celsius temperature. To maintain this temperature, we can maintain the ice bath to maintain 50 to 60 degrees Celsius. Because of both are acids, they provide 100 degrees temperature when it is mixing. So to decrease the temperature, we can place that reaction in the ice bath, and in that condition nitration takes place. So that is generation of our first step is our electrophile generation, HNO3 and 2H2SO4. There is a formation of H3O plus 2HSO4 minus and our electrophile NO3 plus. This electrophile is attacks on the benzene ring and formation of the rhenium ion takes place like this. Electrophile NO3 substituted and this rhenium ion formation takes place, and then the removal of hydrogen takes place and formation of the final compound, that is nitrobenzene. The removal of hydrogen takes place. This is the electrophilic substitution nitration reaction. In the same manner, sulfonation. Sulfonation, we can use only the sulfuric acid, and here also 2 moles of H2SO4 is involved and production of the SO3 ion. It is a electrophilic nature. This SO3 is directly attacks on the benzene ring. It acts as electrophile even though it is having any positive charge. It is having the taking of electron, the nature of taking of electrons. So that's why it is electrophile. and it is itself getting minus charge and benzene is getting the positive charge, and areninum ion formation takes place, and then the loss of proton takes place, and at the end there is a formation of the benzene sulfonate ion. After removal of this proton, benzene sulfonate ion takes place, and at the final stage the H plus is taken from the H3O plus, which is formed in the first step, and formation of the HSO3, that is benzene sulfonic acid. So that is the nitration, and this is a sulfonation reaction, and simple halogenation takes place in presence of the Friedel-Crafts type of reaction, like in presence of Lewis acids like FeCl3, FeBr3. So in presence of Lewis acid like FeBr3 or Fe, any halogenated compound, they produce the X plus ion. This is the electrophile production takes place, and electrophile attacks on the benzene ring, and areninum ion formation takes place, and at the end hydrogen loss takes place, and there is the production of the halobenzene, the substituted aromatic substituted electrophilic substituted benzene compound takes place. So in the same manner, Friedel-Crafts alkylation takes place. Friedel-Crafts reaction means in presence of Lewis acids. The reaction takes place in presence of Lewis acids called Friedel-Crafts alkylation reaction. Here is in presence of AlCl3, RX alkylating agent is alkyl halide, R is substituted on the benzene ring. So it can produce the alkylated compound. In the same manner, acylation takes place. Acyl group, acylinium ion is produced. It acts as electrophile and it attacks on the benzene ring. Areninum ion formation takes place, and at the removal of hydrogen and produce acylated compound. So in the same manner, alkylation and acylation takes place. So this is about the electrophilic aromatic substitution reactions of nitration, sulfonation, Friedel-Crafts alkylation, and acylation. So effect of substituents. So what happened if the already one substitution is present, how it can direct, whether it is orthodirector or metadirector or paradirector. And the second substitution, it depends upon the first substitution. When an electrophilic reagent attacks on the monosubstituted ring, a group that already attached to the ring determines the reactivity and also orientation of substitution on the basis of these two characteristics. That is, whether that atom which is present on the benzene ring or group is electron donating group or electron withdrawing group. So some of the compounds are activating groups. We can say activating and ortho-para directing groups. Activating groups means which can donate electrons to the benzene ring. Electron is stabilized by rich of electrons. If it is having more electrons, it can readily undergo substitution reactions. So the type of compounds are called activating groups, and they always direct the ortho and para positions. And if the deactivating groups are present, that means what happened? Benzene, it takes electrons from the benzene, so it doesn't have any electrons on the benzene, so it doesn't undergo readily reactions to the electrophilic substitution. So that's why it can deactivate. Electron donating groups like alkyl group CH3, OH, NH2. O is having 2 lone pair of electrons, N is having 1 lone pair of electrons. These are the electron activating groups. Alkyl group, OH group, NH2 group. These are the activating groups. But coming to the deactivating groups means NH3 plus, NH3, NHCOCH3, amides, carbonyl group containing amides. Carbonyl means oxygen is very electron withdrawing property. NHCOCH3, NH3 plus. This type of compounds are aldehyde group. It is also having lone carbonyl compound O is a highly electron withdrawing property. Aldehyde groups. These are the electron withdrawing groups, that is deactivating groups. These activating groups are always ortho-para directors, whether deactivating groups are the meta directors. So these can be discussed in the next class.